was solve the equation z cubed is equal to 1. I'll give you our answers in Cartesian form. All right, so z cubed is. I presume you used the Morse theorem for this?
Yes.
Okay.
Can you do this without using the Morse Theorem? Because I know how you would do it if it was like to the 4, because then you could factorize it out and stuff. When it's cubed, it's no, yeah, no, you could still do it, but it'd just be annoying if it wasn't the Morse.
Definitely would be annoying. So z cubed minus 1. Yeah, it wouldn't be easy. You'd end up doing my brain is not functioning today. Too many year 7 classes. What's it called again? I can't remember the name of the formula. Anyway, let's do it using the Morse theorem. All right, Tamara, microphone on. You're talking me through this.
Okay. So z cubed equals cis. In brackets 0 plus k2 pi. So then the 0 just cancel out. So, and then.
So cos 0 plus I sine 0 is your starting point, is it? And then because why is it 0?
Because that's where 1 is.
That is where 1 is. Yeah. Okay, and then you used the Morse, so you're doing cis. Not like cis, but yeah, cos 2k pi or cis 2k pi over 3, is it? When you divide by the 3.
Yeah.
Okay. Plus.
And then you substitute in 0, 1, and 2 into k.
Yeah, what's there? Okay. Okay, so k can be 0, 1, or 2, yeah. And when you put in 0, we should know that one already. So when k is 0, we know your answer is what, Tamara?
1.
Yeah. And k is 1, then you're going to get cos 2 pi over 3 and I sine 2 pi over 3. So what's your answer for that?
Negative a half plus root 3 over 2i.
And then your final answer then, which would be related to that, of course.
Negative a half minus root 3 over 2i.
Yeah. Okay. Sweet. All right, that all makes sense to me. Question.
Sir, I don't remember. I understand why they're conjugates of each other, but why do we end up getting? I don't remember if we talked about this before, but why do we end up getting conjugates when we do this method? I understand why they have to be, but why does doing it like this give you that? I don't. That's just.
You understand? Well, tell me why it has to be so.
Because there's no imaginary part to z cubed, so they have to cancel out somehow. The only way you can do that is by multiplying imaginary conjugates.
Okay. Tell me why this. So you're asking why this method gives you the correct answer?
Yeah. Why does changing the angle like that give you the conjugate of it?
Why does change?
Because we're adding 2 pi over 3 to it.
Well, it kind of, yeah, it's going around in a circle, so...
Yeah.
Why does moving... Isn't it the angle that gives the correct modulus? No, hold on. I don't want to say the wrong thing now. So why does this theory work?
Yeah.
And why do we get... Because... They're like... this. I'm working off screen here.
I've managed to successfully take the class off track.
Huh?
I've managed to successfully take the class off track.
Yes, you have. The angle is the angle that makes the modulus 1. Isn't it?
What do you mean?
Well, you know, like you're developing like almost a triangle here to get to that.
Oh, yeah.
So it bases off that angle.
Yeah.
And that's the angle. So a number of times around that circle, the angle will be 1. It'll give a modulus of 1, which is what we need for z cubed to be equal to 1.
Yes.
And in order for that angle, in order for it to work, it would have to be. Does it have, or just is it just so happens to be?
Is it just a case of it works because it works?
Okay, I know I don't like that. Let me. I need to. Yeah. Let me think about that one. I'll come back to that one on Monday.
Okay.
Let me make a note of that. John always being difficult.
That's what I'm here for.
Oh, yeah. So it's basically, we don't want to know why we do want to know why the Morse theorem works.
Yes.
Well, the Morse theorem is just a repetition of that modulus argument form, the cos or cos theta plus I sine theta, and it's using, you know when you
Yeah, we already proved how it works doing.
Yeah, you get or squared, then you get cos whatever it is, 2 theta plus I, so you add the arguments and multiply the modulus.
So then when you get the roots, it just, well, it would have to give you those answers just based on how you do it.
So, what exact question are we answering again on Monday? That why it is the conjugate that is the pair. No, why it is the angle.
Why does I was like, why does because what you add 2 pi, in this case it's adding 2 pi over 3 each time, right? Why does adding that repeatedly end up giving you that?
I think I've done this before. How did I explain it again? Why does adding this?
But I guess in the case where z cubed or whatever it is an imaginary, it has an imaginary component, then it wouldn't necessarily have to give you a conjugate, would it? Then it could just give you anything.
If z cubed didn't have an imaginary component?
No, if z cubed did have an imaginary component, because then it wouldn't need to cancel the imaginary part, and so it would. So if anything, they couldn't be conjugates, right?
If z cubed equaled something imaginary, yeah? Yes. Then you wouldn't, that's right. Then you wouldn't need to cancel these out. That's beyond the course. But we could, maybe that's a good thing. It would be beyond the course, but that's what I'll do on Monday. We'll investigate when it's imaginary number or more than just 1, perhaps. Maybe I'll look into that, and we'll probably do complex numbers again on Monday, because it's quite a large topic and it's generally quite difficult. Okay, so let's talk about that again on Monday. I'll do something on that, okay? We'll get to just the questions that are in hand at the moment, and then, Sean making me think on a Friday. This is Against the rules, Sean.
Apologies.
All right. Okay. So, question 2 then. Complex numbers W and Z satisfy the equation Z over W equals I. And the W conjugate plus 2Zs is equal to 4 plus 5I. I think that's the question. Now, find both W and Z in Cartesian form. Okay, sorry, it's off screen. Okay, Sean, can you talk me through this one? What did you do? And I'll stop if I disagree with anything.
Okay, so first off, I said Z is equal to A plus BI, and W is equal to C plus DI.
Okay. Yeah.
And then I substituted both of those into the first equation, so A plus BI over C plus DI equals I.
Okay. Yeah.
Then I multiplied out by the bottom and then rearrange to equate the real and imaginary parts.
Okay, so you did that or in some form, and then tell me what your rearrangement is then. What's your...
A equals negative D and B equals C.
Yep, so of course from -1 there, yes, and B equals C. Okay.
And then with the other equation, I substituted what I wrote for Z and W into that as well. So W conjugate would be C minus DI.
Okay, so this
and 2Z would be 2 times A plus BI, and that's equal to 4 plus 5I.
Okay, yep, so that's the 2 bits of information. That's from equation 1 and 2.
I substituted negative D into A, and I substituted C into B.
Okay. And you tidied that up, so I presume you tidied it up a bit. What did you get after you tidied that up? So subbed in.
I got C minus 2D plus 2CI minus DI equals 4 plus 5I.
Okay.
That last one is minus DI.
Minus DI. Oh.
Yep.
Here?
Yep.
Yep. Okay, sorry.
And then equating the real and imaginary, you get C minus 2D equals 4, and 2C minus D equals 5.
Okay.
And then that's just solving the simultaneous equation. So C equals 4 plus 2D, substitute that into C.
Okay, so what's your final answers for C and D?
I got D is -1 and C is 2.
Okay, and then you obviously went back and got A and B.
Yep, and A is 1 and B is 2. So that means Z is 1 plus 2I, and W is 2 minus I.
Yep, I do have the answers, and the answers are correct. Well done. Yeah, that makes sense to me. All good. Tomorrow, are you happy with that?
Yes. Yes.
Did you get it, or are you just understanding it now?
No, I did it. Yes.
Okay, sweet. How did you get on tomorrow? Question 3.
I got most except for D.
Except for part B. Okay.
D, except for part D.
Oh, last part. Okay, same as Sean then.
Yeah.
But I did get it, I think.
Oh, you've got it since?
Yes.
Okay. All right. So let me do this. Okay, so this is the one I haven't done yet. Great. Okay, so if we express, so we have this complex number 4 minus, or 4 plus 4, minus 4 plus that, and we want it in this form, in or is equal to E. Okay, so Euler's form, not minus I, just I. Okay, so, well, this is looking like if you factor out 8, did you factor out 8 or something, or what did you do? Sean, sorry.
Oh, I just I just found the modulus of it straight away.
Oh, you went modulus. Okay. Yeah. So the modulus is what, Sean? 8, is it?
Yep.
Yeah. Okay. So I was thinking. So what I was thinking here is, I want to get root 3 over 2 and a half. I can just factor out 8 out of that. But
Yes.
and I get minus a half then, plus root 3 over 2i, and then I have my angle straight away. But that's, you did the same way. So you just got the modulus and then did the angle off that. Did you like tan with the angle or whatever?
Yeah, I did tan with the angle.
Okay. Tamara, which way did you do?
I did it Sean's way.
Yeah, it's the more systematic way. Yeah, definitely. So you would have got 8 as the angle be 2 pi over 3.
Yes.
So we got, if you want to use your cis 2 pi over 3, if you want to use it in that form first before we get it in that form. And therefore Euler's form is just 8 ei to the 2 pi over 3. Yeah.
Yep.
All right. So Tamara, for parts, that's part A, which was getting that form. Part B, let the roots eat. Okay, so this, all right. This is back
It's the
to
same as one.
Yeah. So I'm not going to I just want the answer to this then. So 4 root 3i. So same thing, you're going to do your 2 pi over 3 and then plus 2k pi, probably all divided by 3 then, is it? So Tamara, what would you guys, your final answers in Euler form? So I have the answers here so I can compare.
2e to the 2 pi over 9i, 2e to the 8 pi over 9i, 2e to the 14 pi over 9i.
Okay, 2e. Sean, are you in agreement with Tamara's answers?
Yes.
I am not.
No?
With one of them. So sorry, your last answer is 14, was it?
Oh, I'm not in agreement with that one. Well, I mean, it's the same thing. You change it to it's allowed because it's illegal.
Yeah, so Tamara didn't look at the range of values, which says between negative pi and pi, not from 0 to 2 pi. So this one, you had to go backwards for this one. So it wouldn't be that. So Z3 then would be, it's the same angle, you're right, but it's not really, it's in the same position, but you've gone the wrong direction. So it would be negative
4 pi over 9, right?
4 pi over 9, yeah. Okay. Does that make sense, Tamara? You okay?
Yeah.
But it's going to get the same position for the, you think you're drawing a triangle next, it's going to be in the same place. So you should have the right answer. Tamara, did you get an area for the triangle?
Yes.
What is it?
Root 3.
Root 3?
Yes.
Okay. Sean?
I put 3 of it.
You got 3 root 3?
Yes.
Yeah, I think you forgot, Tamara, I think you got the area of one of the triangles, but didn't multiply it. So in part C.
Oh, right. Yeah, I forgot to do it 3 times. Yeah.
Okay, I don't need to explain. You have A somewhere there, and B is going to be over here. Let's see. So they're all 2 pi over 3 apart, aren't they? So you can, and we know that the modulus is the modulus 2? Yeah, the modulus is 2, yes. So yeah, I'm just doing this, so if you ever want to watch this video, that we have the solution in half. So there's 3 of these. 2 times 2 times sine 2 pi over 3. But it's 3 of them, okay, and you get, so that's root 3 over 2, and then it's a half of 2, so they're all cancelling out, and you end up just with, that becomes root 3 this time. So it's 3 root 3 is our answer. Okay, so that's part C. Now you're saying part D caused some difficulty. The sum of the roots of Z1 plus Z2 plus Z3. By considering that, show that. Oh, okay. Huh. So, Sean, you think you've cracked it?
I do think so, yeah.
Okay, go for it.
So first off, we have z cubed is equal to -4 plus 4 root 3i, right?
Yeah, not Z3. Z cubed does equal -4 plus 4 root 3i. That's our equation, yeah.
And then we can rearrange that so that it equals 0. And then we have it all on one side. And then the sum of roots is going to be the second term over the coefficient of the second term over the first term. But since the coefficient of the second term here is 0, because we don't have a z squared, that's just going to be the sum of, so z1 plus z2 plus z3 has to be equal to 0.
Yeah, so from the formula booklet, the sum of the roots is this formula, which is the coefficient of the z cubed term, which is 1, or the x cubed term if it was, over the z squared term, and there is no z squared term, so that's 0. So that means that's 0, which means the sum of the roots is 0. So we can say confidently that the sum of the roots is 0, and once we can say that,
we have there's going to be a real and imaginary part, but since it's cos, we only care about the real part. So we can say 2 cos 2 pi over 9 plus 2 cos 8 pi over 9 plus 2 cos of negative over 9 equals 0.
So the real parts of z1, z2 plus z3 does equal 0. So you can then say, so what's the real parts of each? Yeah, as you said, in cis form, you would just take out the cos part, wouldn't you, for the real part?
Yep.
Sine. And it's 2. They're all 2 times, but we'll get to that in a second, I suppose.
Yeah.
2 cos all these angles we had up there.
Yep.
Minus 4 pi over 9 and minus 4 pi over 9 plus 2 cos 2 pi, etc. And then what's 8 pi over 9?
Yep, and that's equal to 0.
Yeah.
And then we can just get rid of all the 2's and
divide everything by 2, yeah.
And cos of negative 4 pi over 9 is the same thing as cos of 4 pi over 9. So that's it.
Yeah. It sure is the same. And we already have, okay, I have it in the wrong order, but yeah, that's it. That's it. Divide everything by 2 and divide 0 by 2. And that's yeah. Okay, so it's just by looking at the real parts. Yeah, well, you did get it. Good stuff.
Yeah.
Yeah, that makes sense to me. Yeah. Yeah, so the key here was to remember that the sum of the roots, there is a formula for this in one of the first few pages of the formula booklet, and it's about the coefficient of this z, whatever the polynomial is, the first degree of the polynomial divided by the second degree of the polynomial will give you the sum of the roots. So that's quite a convenient formula to have and to know, especially, as soon as that you hear sum of the roots in any question regarding a polynomial, you can jump to that one. Okay, so let's go back to tomorrow then for question 4, which is the one I did do before class. My homework. So for part 1, all right, I'll just write a bit of the question for the video. Okay, so A says if Z is I equal to I, okay, so it has no real component, write W in the form, they use cis theta. Okay, so Tamara, did you get it in the W in the form or cis theta? Tamara? Okay, Tamara might be off limits there. Sean, you're going to have to take over.
Okay, so first off, just sub in I into Z. So we have W equals I minus 1 over I plus 1.
Okay.
Oh,
so,
over I plus I over 2I, because it's Z plus I, isn't it?
oh, yeah, sorry. I don't know. Yeah, you're right. So it's I minus 1 over I plus I. I plus I is 2I. Okay. I minus 1.
Okay, and we don't like imaginary numbers on the bottom, so multiply the top and bottom by I.
Oh, yeah, I did minus I.
Oh, but it ends up being the same thing anyway, right?
Yeah. Just thought it'd be nicer. Then okay, so that's 2 over 1 plus I, and you have that as well. And then, so that's Cartesian form a half plus...
a half I. Yep.
Yeah.
And the modulus of that is root 2 over 2. And the argument for that is pi over 4, right?
Yep, so it would definitely be a 45-degree angle, wouldn't it? And you can just work out the modulus then as 1 over root 2 or root 2 over 2. Yeah. So root 2 over 2 and cis pi over 4, because of course it is a isosceles triangle. Cool. All right. Part 2 then. I don't know if tomorrow you're back or you're still gone. Tomorrow? No. Okay. So w to the 14. Okay, so you're going to have to use this to the 14. What did you get, Sean?
Negative 1 over 128I.
Yep. So, yeah, you end up with, this to the power of 14. And which I was using 1 over root 2. Because it's easier to do to the power of 14.
Oh, yeah.
And this pi over 4. And then when you apply the Morse theorem to that, that's going to be 1 over 2 to the 7, which is your 128, as you said. And it's going to be 14 pi over 4, isn't it? Applying.
Yes.
14 pi over 4, which is the same as 7 pi over 2. And looking at that on our unit circle, 7 pi over 2 is going to be pi over 2, 3 pi over 2, 5 pi, 7 pi over 2 is down here, isn't it?
Yep.
So that means its real part, so it's going to be...
Negative 1. Oh, the real part is 0 and the imaginary is negative.
Yeah, so that's negative 1 down here, yep. So the real part's 0, so that's going to make your negative 1i or whatever. Yeah, okay, so yeah, you're right. So that's 128, and that just gives I.
Yep, but it's negative.
Negative I, yeah, sorry. Yeah, I have the negative there. Yeah, so I perhaps would write it minus I over 128, but that's whatever.
Yeah.
Yep. Right, so that's part 2. Part 3.
There is not a part 3.
That's very true. Part B. Thank you, Sean. Part B. All right. This is a lot of manipulation. What is it? A show that? I can't remember.
It is a show that.
Okay. Did you show that?
Yes.
Okay. I'm not going to do that then.
It wasn't a very nice show that, though.
No, but it was just using the conjugate, wasn't it? And then rearranging, just making sure that you didn't make any mistakes algebraically. So it wasn't complicated, but it was, So you just had to form z back with x plus iy and then multiply with conjugate. And then it would tidy up. Part C, find a condition under which, find a condition under which the real part of w is 1. What did you do? Or what's your answer?
I did, based on the thing that we had just gotten, x squared minus x plus y squared plus y over whatever's on the bottom equals 1. And then rearranging that, I got y equals negative x minus 1.
So that's the real part, just, yeah?
Yeah, just the real part.
And then with all this rearranging and multiplying and cancellations, you ended up with what? So I missed that.
Y equals negative x minus 1.
Okay. So that is the condition, I suppose. If y equals negative x minus 1, then it will be real.
Yeah.
The real part will be 1, sorry. Yeah. Yep. So that is the condition. That's the answer, pretty much. C. No, that was C. D. That was part C. Part D asked for state the condition under which W is real and imaginary. So it is real if what?
It is real if plus 1 equals 0.
What?
It's real if that part is 0. If the imaginary part's 0. And the bottom isn't 0.
Yeah. Okay, yeah. I thought you said it's real if 1 equals 0. So this is the imaginary. This is the numerator of the imaginary part. And if that equals 0 and
the bottom part doesn't equal 0.
Yeah, and x squared plus y plus 1 squared does not equal 0, then they're the conditions for it to be just purely real, isn't it?
Yep.
And then something similar for so it's imaginary if this bit equals 0 and the denominator doesn't equal 0 and
the real bit is 0.
Yeah, same thing. Yeah, so you just have to state that. So I presume you can do that. Part E. Okay, part E. Find the modulus of z given the argument is pi over 4. Okay.
I thought that would just be 1 since we had pi over 4 before, and the argument for z in that case was 1. I mean, the modulus, sorry, was 1.
Yeah, it is 1. Yeah. Yeah, you could go about it and say tan is, and use these things, the real over the imaginary. That's what I did, just to show it. The tan of the argument then is the imaginary over the real, wouldn't it? Sine over the opposite over the opposite over adjacent. So the real part, the imaginary part is that x squared minus x plus y squared. Obviously the denominators have cancelled already, and the tan of the argument then is 1 pi over 4.
Yep.
Then a rearrangement of this, bring that over that side, and then cancel out, and you end up with x squared plus y squared equals 1. Getting the square root of that. Once there's the modulus there.
Yeah, okay.
That perhaps, what was the wording of the question again? Did it find the modulus of z?
So it just said
it's 1. Okay. Well, you're not wrong. Perhaps they could have they show that the modulus of z maybe instead of find, but yeah. Okay. All right. I think we're pretty much out of time. We'll look at complex numbers again. I'd like if you could find some questions from the book from this one, because there's definitely some doozies in there.
Yeah.
And put it in. So perhaps spend some time on that. Not going to move on to proof by induction and induction until Tuesday's class. So just going to stick on complex numbers, and I'm relying on you guys. I don't know if tomorrow's still there or not. I'm going to rely on you guys to come up with some from the book.